Hello friends, welcome to Electrical Design Engineering YouTube channel. This is our lecture number of 47, almost of ETAP course. This is a free ETAP course going on this channel. And in today's lecture, we are going to study about the starting of induction motor using starters in ETAP. In previous lectures from lecture number 40, we are discussing the modeling of induction motor in the ETAP software. And in today's lecture we are going to study about the starting of induction motor using starters in the ETAP. First of all, we should know what is the function of starters, why we need the starters, why we use the starters in starting of the induction motor, and then we will see how we can use the starters in the ETAP software, what are the starters available in the ETAP software, and then we can generate the graphs of different like slip speed graph, current graph, voltage graph, motor torque, acceleration torque, load torque. All these graphs will be generated and you can see what we can understand from these graphs, what information we can obtain from these graphs. So let us start the today's lecture. Induction motor, as you know, the induction motor draws very high starting current, almost 5 to 7 times when they started directly without the any starter. That means at induction motor at the starting draws 5 to 7 times of the rated current uh, when we start the induction motor directly. This high current or high inrush current causes voltage dips in the power system. These voltage dips cause stress on cables and switches and other equipments because there is a large voltage drop at the starting of the induction motor, and this voltage drop causes malfunctioning of other equipments connected to the system. To reduce the inrush currents, motor starters are used. So our main purpose of using the starters is to reduce the starting current. The various starters used are auto transformer starter, star delta starter, rotor resistance starter, starter resistance starter. These are the main starters which I have studied in our BTech and MTech course, and master's course or a bachelor's course. And among these starters, most commonly used starter is the star delta starter. Okay, as you know, the motor at the starting behaves as a constant impedance load, so current is directly proportional to the applied voltage. At the starting of the induction motor, the motor behaves as a constant impedance load. That means their impedance remains constant. Now the question arises here, why it behaves as a constant impedance load. If you want to know why it behaves as a constant impedance load at the starting of the induction motor, you can comment on this video and I will make the video about why the uh, induction motor behaves as a constant impedance load at the starting. See, this is the formula, the simple Ohm's law. V is equal to I Z. When Z is constant, when Z is our constant, when Z is constant, that means when Z is constant, if Z is constant, so I is directly proportional to V. Okay. To reduce the starting current, we have to reduce the applied voltage. Now, voltage is in our control and current is the response of the voltage. So, in order to reduce the current, what we reduce? We will reduce the voltage. When motor attains the 80% of the speed, the full rated voltage is applied. We cannot run the motor continuously on the reduced speed. So, when motor attains almost 80% of speed, then we can shift our um, then we can apply the full voltage, because at the 80% of speed the sufficient back EMF has been created. At that time the current will be very low, not as compared to as starting current will be very high, but when the motor attains 80% of the speed, at that time the current will be low, and the voltage be very low, and we can apply now the full voltage. This can be done using starters. What I have already told that in the starters, start the motor at reduced voltage. After attaining 80% of the voltage, we are removing the starters and we are shifting the motor to direct online starting to direct online. That is, we are applying the full voltage. Now this is the auto transformer starter. I can adjust 1 minute, or I can keep it this side. This is the auto transformer starter. This is the auto transformer. Here you can see, here is the auto transformer. What we have done, we have first started the motor from here. This is the start position and this is the run position. Okay, and when starting, we kept the switch here and start the motor through the starter through the auto transfer. This is the auto transformer. We cannot apply full voltage, we apply the reduced voltage, and we can control the voltage by using the tapping on the auto transformer. And then what you can see one thing, when switch is here, when switch is at this position, what is the path of the voltage? The power voltage goes like this toward this, and then from this, and then like this. Okay, that means I want to understand you that at this time the voltage goes through the starter, and here the voltage at this point, the voltage is reduced at a the voltage is reduced as per the tap setting of the tap setting of the auto transformer. Okay, and when the motor attains 80% of the speed, then we can reduce we can change this switch to the run position, and at the run position we are applying the full voltage. You can see here we can apply the full voltage when the motor is running. Then the path of the voltage will be like this. This is like this, and here it goes to this and here. Now you can see the auto transformer is now removed. Now the voltage is directly applied from the supply. That means we can apply now the full voltage. Okay, now we can see what is the effect of applying reduced voltage on the induction motor, and what is the effect of the reduced voltage on the starting of the induction motor, on the starting torque and starting current. Here that let X represents the tabs setting on the auto transformers. Suppose we are capping the auto transformer at 70% of that tapping, so the voltage applied will be 70% of the full load voltage, and V is the full load voltage per phase, and Z is the equivalent impedance per phase. Okay, as direct online starting, when we are applying the full voltage, our starting current will be V by Z. Simple Ohm's law, V is equal to IZ. Also, starting current will be V by Z. When we using the auto transformer for starting purpose, then our current at the time of using the auto transformer, X is equal to X divided by Z. X is the percentage at which we have set the auto transformer. Suppose X percentage of the voltage we are applying, then our current when we use as a auto transformer as a starting will be X by V by Z. V by Z is here equal to the IST, so we can replace here V by Z by IST, so it becomes X by IST, that is X times of the starting current when at the time of full load. If there is 100% starting current at the time of full load, at this time it is only 70% of the full load current. Now in torque, what will happen? This is the torque compression. You have studied about in your BTech and MTech course that starting torque is directly proportional to the V square. So when V is equal to the X times of the V, that is we are applying reduced voltage X times of the V, we are applying X percentage of the V, then our auto transformer at the time of using the auto transformer, our starting torque will be X square times of V square. Here V is directly proportional starting torque, so X is equal to T auto is equal to X square times of T starting. Okay, you can understand now. But that means here the torque gets reduced x square times. Here the current gets reduced x times, but here the starting torque gets reduced by x square times. Now we can see the another starter, that is star delta starter. You can see this is the three phase RYB, and this is the switch, main switch, and this is the delta connection here, and this is the star connection here. Okay, you can see one more thing we have written here, starting star, star starting. That means we are starting the induction motor at the star connection, and when it attains 80% or 70% of the speed, we are shifting our connections to the delta connection. We can see here it is written here delta running. Okay, now why we apply a star connection at the starting? Because in the star connection V is equal to root 3 times of Vp, per phase voltage is equal to 1 by root 3 times of VL. Here we are getting the reduced voltage per phase, because here the per phase voltage is 1 by root 3 times of VL. This is a simple concept of what you have studied in your BTEC. This is nothing but that means here X is equal to 1 by root 3. So our starting current becomes x times of uh, I starting. So and torque becomes 1 by 3 times of the V, 1 by 3 times of the starting. I will show you this thing in the Excel, so that you can understand what I am actually want to say you. This is the Excel sheet. Whatever I am saying, that this is at 100%. First, we are applying 100% of voltage. We are not using the starting devices. We are applying a 100% voltage. At that time, suppose our LRC is 453.51 and our local total torque is 335.51. Okay, this is the condition at 100%. I have used the induction motor where LRC and LRT is same in the ETAP, so that you can compare the results what we have calculated in the Excel sheet. We can compare these results with the ETAP results. Now suppose we are applying 80% of the voltage. You can see the LRC gets decreased by 362.8. This was, I have kept this is the 100% condition. I can write here, this is at 100% of the voltage. Okay, when 80% is applied, our starting current gets reduced by x percent, that is 80%. So you can see we have used your formula. You can see here the formula 0.8 into f ft, what is 100%, this f, that is the 100%, it becomes equal to, you can see xk, we can 368. Similarly, you can see here, you can even calculate from your calculator that it is x square times of this full load, x square times of the full load. Suppose now in the starting what is star delta starter, our x is 1 by root 3, that is this is 1 by square root of 3, you can see here, and it is equal to 0.57735, that is 57.7%. We can write here 57.7%, and you can see the starting current becomes 261 times. First it was 435, it gets reduced to 56%, that is becomes 261.6, and starting target was 35%, and because it is now 11%, it gets reduced to 11%. Okay, now in the next lecture we can use these values in the ETAP, and we can run two things. One is auto transfer starting and star delta starting, and you can see these results match with this results, and we can also generate the different graphs there.